Okay, welcome to the second to last lecture. I am so sad we are almost done, but also I'm happy that the quarter is almost over. We are so close to the finish line. Hang in there. We're really proud of all of you for everything you've learned this quarter. We've covered a lot of ground. This is only a 2-unit class, but I hope you feel like you've taken a lot away from it. If you get a chance, please fill out the course survey on Access. We'll also have an unofficial course survey, like a Google form. I'm curious about some more specific things about what you thought about this class and maybe like how the material can be integrated into other classes. But the Access survey is much more important for this class than it is in many others, because this isn't like a bona fide sponsored class with departmental support. This is kind of just a small thing that Armin and I wanted to teach last year, and then Julio took it and was interested in teaching it with me this year, and I'm graduating, so who knows what's going to happen. So if you feel like this material was important for you, like please indicate that, so that maybe others in the department will be interested in like picking up some of the material, or maybe picking up parts of the class. And then also, if you feel like there were things that we were missing, that we left out, or that maybe we could have improved teaching-wise, definitely let us know that as well. So if you get just like 3-5 minutes, this would be a huge help for us in the next like week or two. So yeah, just a heads up there. All right, so we're picking up where we left off at the end of last week. Last week, we were kind of talking about how threads are great and they allow us to have concurrency. Yeah, there's a lot of like problems that you have to watch out for, but concurrency is just hard in general. And I would say that threads as a model are not terribly difficult to grasp. It's easy to understand what's going on. You just have multiple trains of thoughts. You have to watch out for concurrency issues, but like understanding what's happening is relatively straightforward. But if you need a very high degree of concurrency, we start to run into problems, because let's say that we wanted to talk to like 5,000 or 10,000 clients on a server at the same time. If you have one thread per connection, you start having issues, because there's a limit to how many threads you can have based on how big how much memory the stack will take up. And also context switches can be pretty expensive if you are getting onto the CPU and then you're waiting for like IO, you're waiting for some incoming message or something to send or something, and you're not actually doing much on the CPU. So you get onto the CPU, as soon as you get there, you switch off. And because you're on the CPU for such a short amount of time, your time is, you spend a lot of time just switching between threads and doing context switches and not actually doing anything productive. And it would be better if you could just have one thread that stays on the CPU and does more stuff for a longer period of time rather than constantly switching between threads. We talked about this thing that you may or may not have heard of from 110 or 111 called event-driven programming, or sometimes non-blocking IO. And this allows us to kind of like look at a set of file descriptors or a set of things at the same time and sort of get a notification whenever we need to do something with a file descriptor, and then we go to that file descriptor, we read the data, write the data, do whatever we need to do. And it's nice in theory, like this would solve our problems, but we have a very difficult time managing state associated with each of the things that we're looking at in this set. And so if we're like, I don't know, partway through reading from a database, and then we have to remember, okay, I'm in the middle of reading from a database. Here's what I've read so far. Read some more stuff, append it to that. Oh, I was talking to this client. I have to send this data to this client now. And it's kind of like cooking in a kitchen with 10 dishes going at the same time and trying to remember everything, what's what. We talked about this idea called a feature, which allows us to, it's kind of like a little helper that allows us to encapsulate the state for some ongoing operation. And if we have a bunch of different features at the same time, we can just go through and say, hey, which feature needs attention? Give it attention. We call its Paul function. The Paul function is what actually does stuff. So we just call Paul, and then the feature does its thing. And then we come back and we say, hey, this other feature needs some work. And we call Paul, and the feature does its thing. And from the point of the thread that is calling Paul, you don't need to know anything specific to what the feature is doing. You just have to know, oh, hey, this feature needs attention. I'm going to call Paul to give it attention. This other thing needs attention. I'm going to call Paul to give it attention. So we get much more encapsulation, because when you're implementing this like event loop, you don't have to be thinking about the specifics of what is going on. And then when you're implementing the feature, you only need to think about your one individual task. Like, here's my state for this particular thing. I don't have to think about anything else that's going on at the same time. This is a big improvement, but it's still not quite where we want to be. So I'm going to spend a little bit more time recapping features just so you make sure you understand this, and talk about some of the like syntactic issues that come up with this, or syntax issues, or whatever the word is. And then we'll introduce some new syntax that makes this a lot easier. And this is the syntax that most people use. Most people do not actually write features themselves. So just quick recap. What are features? Let's say that we have, or actually, so here, you can think of a feature as a helper friend that oversees each operation, remembering the state that's going on, like I mentioned. So you might have a feature that is specific to cooking a piece of meat, and it keeps track of like how much time has elapsed, when we need to go and flip this thing. When we flip it, it remembers that we have flipped it. And then when we're finished with that, then we're done. And like I mentioned, you can kind of be juggling many different features at the same time. So you have an executor thread, which is implementing this event loop of like, wait for something to need attention, figure out what needs attention, go to all those things and give them attention, and then repeat and recycle. So that's kind of what's happening in this thread. And we have our features over here that are specific to the tasks. These features can kind of raise an alarm. They call this wake function that alerts the executor that they need attention. And then the executor goes there and will, just do whatever needs to be done. Go back to sleep when nothing else needs more attention. When one of these features needs attention again, then it goes and does the thing. If the feature is completed and it has like produced a result, then the executor thread will see that and it can take the result and do whatever it needs to do with it. But this process kind of just continues until the executor is done with anything. Any questions about this kind of like overall design? Any questions come up over the weekend? So I mentioned that nobody actually implements features like from scratch unless you're working on a low level library. Most of the time there are like a set of primitives that are already implemented, and then you just build features on top of features. So I linked to a list of different combinators that you can use. For example, there's this .then combinator where you can say place on stove. Let's say that this function returns a feature. So once that feature is done, then take whatever its output was, this meat thing, and pass that to cook one side, which is going to produce another feature, which is going to cook one side. And once that's done, take the output, pass it to this next feature, and then take the output and pass it to this next feature, so on and so forth. And it's kind of like features all the way down in the sense that this is building up one feature, like the let feature equals, is building up a feature that does all of this. Internally, this feature is keeping track of how far along we are. Have we done this step? Have we done this step? Where are we? So here, one side cooked, time to flip. We did these two steps already. And when the executor thread calls Paul on this feature, well, it remembers this. And so then it can call Paul on the appropriate like child feature, I guess. And then this feature does the same thing. This feature might be composed of several other features, and it will remember how far along it is and call Paul on the appropriate thing. Any questions? So this works, but it's not very fun to use. Like, this looks okay because it's relatively simple. Like, this code does work. And I would point out that this is already a big win over manually dealing with like callbacks and state machines as you would if you were writing the like C and C++ code with the system calls like epaul and non-blocking read and write and whatnot. So this is okay, but it's still not great. So it's a little bit clunky to type all of this stuff out. We've got like all these Lambda functions. You have to be looking at all these parameters and stuff is getting passed around. This is a very, very simple example. Like, this is about the simplest that you can get. But if you start writing more complicated code, then the complexity increases. And there's an additional problem, which is kind of specific to Rust, that let's say that you had some like some local variable up here, some mutable local variable that you needed to use in all of these steps. I don't know, maybe it's in this analogy, it's like a spatula or something, or like some salt or seasoning or something. And you want to use that variable in all of these. Well, that kind of becomes a little bit difficult, because if you are trying to capture a reference to that thing, well, then that's problematic, because these are Lambda functions here. These three things are Lambda functions that like take the output of the previous feature and then provide the next feature. And Lambda functions, if your thing is mutable that you're dealing with, then you can only have one mutable reference at a time. And if one Lambda function gets that mutable reference, then the others can't get that mutable reference. And so there are some workarounds for this, but it becomes a little bit ugly. And this is just more stuff than we want to think about. Like, is there a way that we can simplify this so that we don't have to think about all that stuff? We can just write the rest that we're used to writing, and it will just work. To give you an example of a slightly more complicated example, let's say that we have some function which is, let's say we're implementing a mail server or a chat messaging server. And so we're receiving a message or an email from one user, and we're trying to deliver it to the recipient, to the destination user. And so in this function, we're taking an email ID. It's just a number that represents like which message we're trying to deliver. We are taking a recipient ID, which is the ID of the destination person that we're trying to deliver this message to. And we go through a few steps. So first of all, we load the message. Maybe this message is being stored in like a database or something. Maybe we're in the process of receiving it from the client, and so we're receiving this over the network. But we do something that is loading a message that is potentially going to take some time. There's some I/O involved here. We have to like receive some parts, then maybe wait for the network to catch up, and then we receive some more parts. But there could be some delay here. Once we have the message, so this is going to give us a message object. So we took this ID and we loaded the full message object. Once we have that, we're going to load the recipient for this. Like we have an ID, but we need the full recipient. And so maybe we do the same thing again, where we load this recipient from a database. This could also take some time, so it's returning us a feature here. And then there's this map function. Let's say that we want to take this recipient and just make sure that they have enough space to receive this message. I don't know, back in the days when inboxes had small amounts of space, I guess they still do have finite space. If this message is large, you want to make sure that there's enough space for this person to receive it. This is not a blocking, this is like it's just an if statement. Like if recipient dot space is like larger than message dot size or something. There's no networking or anything that needs to be done here. So this is actually not returning a feature. This is just returning a result. That's why this map thing is used here. It's saying like, there's no then, because you don't have to like wait for this next step. It's just like, hey, take the output from this previous step, do the thing, and then just go to the next step. Once we verify that there's space, then we add it to the recipient's inbox. And maybe this involves some database calls and can be a little bit slower. And so this is returning a feature as well. So that just took me like 2 minutes to explain like 5 lines of relatively self-explanatory code. And there's some specific things here that I don't love. So there's actually like 2 different kinds of functions happening here, right? We have several functions that are returning features. These are implemented asynchronously. So they're implemented using features where like you do the thing, the feature says, hey, I can't make any progress right now, come back later. Then you come back later, and then it does some more progress, and then it says, hey, come back later, so on and so forth. We also have a synchronous function here, like a normal function, like the kind of function that you've been seeing all quarter in Rust. And you have to use like and then for these features, and you have to use map for this other one. And it's kind of a lot to remember and keep track of. Also, this function signature is quite a mouthful, like impl future output equals result. What this is saying is that, hey, this function here is constructing a feature. It's building up a feature. It's going to return you a feature that is returning a result. So it can potentially fail. Like if any of these database calls fail, or if there's some network issue or something, then we might get an error, or it might succeed. This is our output type. But it's kind of a lot to type. It's also a lot to remember. And then there's this really strange decomposition here. I don't know if anyone noticed this. But if we have a get recipient call that is supposed to load a recipient from a database, why would it need to take a message? Shouldn't it only need to take a recipient ID, just like loading a message only needs to take an email ID? Why would we have to pass a message here? Yeah, it's because the next 2 steps require both a message and a recipient. And because this is kind of like a pipeline of sorts, where you have one step that outputs some data, which you feed into the next step. This is the input from the previous step. And then that produces some output that feeds into the next step, which produces some output that feeds into the next step. Because it's written as this pipeline, any information that you need later on needs to be carried on as part of this pipeline. Like, we need to preserve both the message and the recipient ID, even if we don't really need it now, just so that when this returns something, we have both the message and the recipient for the next step. And this is just bad decomposition. Like, I don't want to be writing functions just like this, or I don't want to be writing functions like this just because the caller needs some extra information. Like, this message thing is not important for the implementation of this function. It shouldn't be part of the interface. It's only part of the interface because the way that this function is being used in this very specific scenario requires it be designed like this. And that's not so great. We hope to do better than that. So there is some, it's called syntactic sugar. Like, it's compiling down to the same thing, but it just makes our life easier with some extra syntax. We could take this function that we just had, and for this function signature, I mentioned this is kind of long. We can replace it with this function signature. Notice this async, and then this like return type is a little bit different. So an async function is a function that returns a feature. So if you have like several features inside of this function, the compiler will chain them together for you with the appropriate combinator. So you don't have to think about, okay, I need to use and then here, and I need to use map here. If you had something in here that did not return a result, and then is for features that return result. If they don't return result, you need to use a different combinator called then. And it's just like, it's a lot to remember. If you write this async function and you have some features that are inside of here, the compiler will just chain them together for you. And you can just write the like output type that you intend to return, and the compiler will transform it to be this. Really, like, this is a function that's returning a feature. That's what async means, and so it will write out the like impl feature output equals blah 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 for you. And then all of this stuff inside of the function, you can just write it like you would write normal code. The only difference is, so for example, like here, this was just a normal function call. Here in this async version, you just write it like a normal function call. Nothing has changed. The only difference is that when you are trying to use a feature, so load message is a function that returns a feature. Load message doesn't actually go and load the message right away, right? This is the idea behind these features, is that load message is generating a little purple helper for us that is going to do the work. And we call await to say, hey, wait for that helper to finish and like load the message and then get me the result. Okay, so you can only use await in an async function or block. Like, when you call .await, what it's doing is it's transforming it into this combinator sort of thing. But this allows you to write code that is almost the same as you would normally write. And then another win here is we have no more wonky decomposition. You can just like define variables, and you can use those variables later on without having to make sure that they get piped through this weird pipeline correctly. Okay, so you just say let message equals load message, let recipient equals get recipient. It's a very natural way to write this code. Under the hood, the compiler compiles it down to something like this. Everything else is pretty much the same as what you're used to. Any questions so far? I'm going to talk about like how the compiler actually compiles this. So if you're curious about that, you can save that. But any questions about the syntax or like how you're supposed to use this? Yeah. So if you did not await this very last thing, then sort of like the return type of this function, if it were a normal function, would be a feature. And the compiler would complain because it's saying, hey, you said you were producing a result, but your last line is producing a feature of result. You probably want to await that because that's not a result. If you didn't have this return type here, like if you put a feature of a feature here, then that would successfully compile and you'd be returning a feature of a feature, which is really weird. But it is possible. But yeah, great question. And we'll talk about how this works, but the compiler transforms this to to it generates a feature with a poll method that is very efficient and just about as good as you could do by hand. So this makes life really easy. And I'll just walk you through the process of converting some synchronous blocking normal code into this like asynchronous non-blocking futures-based code that uses purple helpers all over the place to keep track of state, but under the hood is really using something like epoll and non-blocking reads and writes to be very, very efficient and lightweight. So there are a couple of steps that you go through, and I'll just outline those. Here is some code. This is a very, very, very simple echo server. So what this does is first it kind of like moves into the apartment number 8080, and it like sets up shop. And then it waits for somebody to knock on the door and add themselves to the waiting list. That's what listener.accept does, is it blocks, it waits until somebody comes. And once somebody comes, then it returns to us a socket. This is like basically a file descriptor under the hood that we can use to talk to that specific person. And we spawn a thread to talk to that specific person. We read what they say to us, and then we just send it right back. It's a basic echo server. So how do we make this into a non-blocking echo server, like an asynchronous echo server that can handle thousands and thousands of concurrent connections? Well, first, what we do is these things that we're using here, for example, like TCP listener. TCP listener is what we called accept on. This is like how we're moving into the apartment and waiting for things. This is a blocking version. Like if you call listener.accept, that is going to block. And that's what we're trying to avoid. So you take these libraries that you're using and you replace them with non-blocking equivalents or asynchronous equivalents. And this is one of the like very strange things about the asynchronous world, is that like there's a totally parallel universe where like all the libraries that you had normally, you kind of have to have non-blocking versions of those, because we mentioned last time, if you are in a future, if you're like inside of a poll function and you call a sleep function or something that is going to block and take you off the CPU, that's taking the executor thread off the CPU. And the executor thread is not going to be able to do anything else. It's not going to be able to run any of the other features because you just put it to sleep. And so it's really important to use like non-blocking versions of all of these things. And so we replaced TCP listener. This is now a Tokyo TCP listener. Tokyo is the library that that you'll use. It's the most popular library for doing asynchronous programming. We replaced it with the non-blocking asynchronous version. And we also replaced thread spawn with Tokyo spawn. So instead of spawning a thread, we are basically spawning kind of a future. It's sometimes called a task or a lightweight thread that is going to do this work. And the syntax is pretty similar. What was this? Oh yeah, okay. So we just replaced those versions. And so now we have features, right? TCP listener.bind, that is waiting to like move into the apartment. That's a feature. TCP listener.accept, that is returning a feature too. And so you need to make sure that you await these features to actually get the output, right? This would not compile if you just said let mute socket comma underscore equals listener.accept dot unwrap. Actually, you couldn't even call dot unwrap on listener.accept because the compiler is going to say, hey, listener.accept is returning a feature, not a result. You can't call unwrap. You have to call await first to say, hey, wait for this feature to actually finish and get the output, and then unwrap that. And then you're only allowed to call .await inside of an async function, right? Await is starting to do this like chaining of features and like pipelining things together under the compiler. It doesn't really make sense to await something inside of a synchronous function. This only makes sense inside of an async context. And so we have to make sure that you add these async things to convert everything into something that returns a future. And the very last thing that you need to do is you need to tack on this like Tokyo main macro above your main function. What does that do, and like why is that necessary? Well, our main function now, because we declared it async, the return type of this main function is a future. Like you can just execute your main function and it's going to return you a future. And if you didn't have this, like you could run your program and your program literally wouldn't do anything. you would run the main function. It's going to create a feature that when polled does the program. But if you don't actually go and poll it and like submit it to an executor and do something with it, then your program won't do anything. Like you'll run your program and it will create the feature and return the feature. That's what this async main function does. And then your program's like, hey, I'm done. Like I built the feature and I returned it. And then it's just going to exit without doing anything. What this Tokyo main macro does is it like does some extra code transformations that calls main, takes the feature that it returns, and then submits that to an executor, the Tokyo executor, which then goes and repeatedly polls that feature so that your whole program runs. Remember, features are composed into like chains of features. And so what your code inside of main is doing is it's just generating like a giant feature that is your entire program. And so this, when you submit it to the executor and the executor repeatedly polls it, that is what is running your program. And to sort of emphasize this point, because I think it's very strange when you see this for the first time, let's say that we have some async function add to inbox. It's the async version of the code that we were looking at earlier. Looks like normal code, but if you run this function, it will not actually do any work with any messages. It is not going to load the message. It is not going to get the recipient. It's not going to add to inbox. Nothing that we have written here is actually going to happen, right? This is still a function, and you can still call it, but the purpose of this function is not actually to do all of this work. The purpose of this function now is to return a future that will do all of this work when it's polled. It's returning a feature that does the stuff that was written inside of this function. This is really weird, but if you think about it in the context of like, you know, the picture of the kitchen that we had before, it sort of makes sense. Let's say we have a main function and we have this add to inbox function, and main says, hey, please add email X to recipient's inbox Y or something like that. And add to inbox says, say no more. Well, what this function is doing, like if you actually run this code, it is creating a feature composed of little features like load message, get recipient, add to inbox, that will do that work, but it's not actually doing the work right away. It's returning this feature to main. And if main were to execute this feature, then that work would happen. So main has to actually go and submit this feature to the executor thread, which will go and actually do the work. Now the email is added to the inbox. This is really strange. I want to stop and ask if anyone has questions here or any clarifying comments. It's like really bizarre. You can write a program with like tens of thousands of functions. You run the program. At the very beginning, your entire like I guess program, like all of the functions that you wrote will run, because they're all like generating these features and parent features and sub features. They're generating this this program in terms of features and returns it at the very, very beginning of the program. And then when you submit it to the executor thread starts polling that feature, and the poll implementations are what contain this actual code that will go and actually do useful things. So let's talk a little bit about how this works under the hood. And there's a lot to talk about here. Like I am not even going to skim the surface. Part of the reason that this took so long is because there was a lot of difficult compiler work to make this happen. But I want to give you a sense of like, how does the memory work? Like, where are these variables being stored? Just so you have a mental model when you're writing this code of like, okay, what is the computer actually doing for me? Right, so async code looks very normal. It looks almost the same as code that you would normally write. Well, under the hood, it's completely different, like not even remotely the same. Let's say we have this normal synchronous version of add to inbox, right? This is the code that you would have written last week if you were writing something like this. And normally when you're writing synchronous code, any state is stored on the stack or maybe on the heap, but you have pointers to that on the stack. And if we are in some function called like make, or we're in add to inbox, maybe this calls get recipient, that calls make database request, and maybe, you know, there are some local variables at every level here. They're all stored on the stack. And if you have functions calling functions, you know, you just have more stack frames. And if we need to wait for a moment, well, we just leave the stack as is with a bunch of stack frames, and then the OS will switch to a different thread with a different stack. So, you know, you take that memory, swap it out for something else. if we want to look at the asynchronous version of this, so it looks almost identical besides the async here and the dot awaits here. That's really the only difference. But this function is returning a future. And that means that any state for this operation needs to be contained within the future object. Right? We said futures are these like helpers that keep track of like what you're doing, where you are, what you need to do, and it all has to be self-contained inside of this object. So there isn't really like a persistent stack that we can use here because everything needs to be inside of the feature. This is like how things are defined. So what do we do? Like, how do we take code that looks like this and compile it to something that we can actually run like on an x86 processor? If you look at this code, there are 5 places where we might be paused. So the only time that we really need to store state is when we're switching to some other task, right? That's actually the only time when you need to be remembering things is when you're like no longer on the processor, somebody else has the processor. So you need to make sure that when you come back, you remember what you were doing and like and what to do next. So when we think about how to store the state, we only need to be looking at the places where we are not on the processor, where we could be potentially, yielding to some other task. And there's 5 places where this can happen. Number 1 is before anything happens. Before we start executing anything, like we're not on the processor, if the feature has been created, it will have been provided some parameters here. So we do need to remember these parameters, but nothing has really happened yet, so we haven't been polled yet. If we have called load message, but this hasn't finished yet, like we're in the middle of waiting for load message, then we're going to have some state, right? Load message might have some state. This is going to return a feature that is like in progress. So we'll have some extra state there. If we are waiting for get recipient to finish, then we could potentially not be doing anything here and we need to remember some state. And if we're waiting for add to inbox to finish, then we wait here as well. And then the last place that we could have is we're done. So we had some results, like it might have succeeded, it might have failed. We have some output, the feature has completed, and we just have to remember that until like the poll method is finally finished and we return whatever that was. So there are 5 possibilities here. We can actually use an enum to store the state for these possibilities. Enums work really well for this purpose. We're either here or we're here or we're here or we're here, that sort of thing. If we're at the beginning, I mentioned that there are 2 things that we need to store. We just need to store the parameters. That's all we care about. Like we can actually go through and say, okay, at each state, what is it that we need to remember? At the very beginning, we need to remember the parameters. We're going to need that for the rest of this code. Over here, if we're waiting after load message, what do we need to remember? Well, we haven't really gotten anything out yet. Like that was the very first thing that we were going to do and it hasn't finished yet. So we still store the email ID and the recipient ID, but we also need to store this load message feature because actually, I think there's an error on this because after this point, after this await, I don't think we use email ID again. So I think we can delete that. That's an error in the slides. So in this state here, we need to store the recipient ID because we use that later on. We also need to store the state of like wherever we are in loading this message. Load message is returning a purple helper that has a state of its own. It has some progress there, and we have to remember how far along we are with that. After this, get recipient. Like if we're here, we need to remember the state for that, so on and so forth. At this point, we don't need the email ID anymore because we've already fetched the message. So we can store the message itself. We don't need to store the email ID anymore. We do still need the recipient ID. Actually, this is another error. We're not going to use it after this point, so get rid of that. Let me just update these slides so it's not confusing. Here, we don't need this. And here, we no longer need this. It's already been incorporated into that feature. And this is going to change over here. Okay. So yeah, after here, sorry. After this point, after we're like waiting on get recipient, we need the message still. And we're going to get the recipient eventually once this feature finishes. After that point, we need both the message and the recipient in order to do like recipient.add to inbox message. And we're also in the middle of like waiting for this. And then when we're finally finished, the result is just, success or failure. Does this make sense? Actually, I made the same mistake on this last one. Let's remove this because if we're awaiting adding to inbox, then we've already kicked off that feature and we've done the stuff already. So we don't need any of that. Sorry, I made these slides like half an hour ago. Okay, so that's how we could store the state at all these various points. By the way, did anyone have any questions about this? So I guess it's not quite equal to the largest size. It's like very slightly bigger. But yeah, you're right. So this is how we store the state. That's fine, but we still need to provide an implementation now. Like you can't just remember things. You need to also be able to execute this code. So how do we implement the poll method? Well, what we can do is we can have a poll method that just matches on the current state. And depending on where we're at, you just run the next bit of code. So we have, there are like 3 things that need to be done here. Like at the very beginning, we have to call load message. And then once that returns something, then you apply the question mark operator, maybe return early, then kick off get recipient. Then you do this next piece here. And you end up with a very ugly chunk of code. But if you look here, there is this is pseudocode, by the way. This will not compile. And this is also not exactly how this gets implemented under the hood. It's a good match for how things are working conceptually, but the actual implementation uses a language feature called a generator, which delves into a bunch of territory that I don't want to get into right now. If you're curious, one of these 2 links is a really good blog post that overviews things and like shows some code. And there's also a really good video from a conference talk that walks through this. But conceptually what it's doing is it's saying, hey, where are we right now? If we haven't yet started, then let's call load message. That's going to produce a feature that is going to go and load message. And so like kick that off. And then store in our state that, hey, we're waiting for load message. You store the recipient ID and the load message feature that we just got back, this next feature thing. If we get polled later, and then we see, hey, we're in load message state, then you say, okay, well, let's get the message, like poll this load message feature from before. If this finished and this gave us back a message, then we can do the next step. We can, get the recipient. So we store this message, let message equals. We store that inside of the state, but then we can call get recipient, and we switch to the waiting get recipient state where we have a message and we're waiting on this line here. Let recipient equals get recipient. If we're in that state and we get polled, well, we just poll the thing again. We poll this feature again, and if that finished, then we move on to this yellow block here. And if that is still waiting, then we just keep polling that, so on and so forth. But the compiler is basically taking the code that you wrote here and putting it into a poll function for the feature that it's producing. This is a pretty complicated slide. Does anyone have questions about how this works? There's also a little bit of hand waving, just because the code is actually pretty complicated and ugly. That it produces, but this is why we're using syntactic sugar instead of trying to write this ourselves. But I want you to have some conceptual understanding of how this is running on your behalf. Between load message and add to inbox. So let's see, load message. It does get stored inside of this waiting get recipient state. So if we go, we finish this, that kicks us off into this red block here, where we're like running get recipient. So get recipient is in progress, but we also store in the state message. Then once we transition from this state into this state, we don't need to store the message anymore if we're waiting for add to inbox. Because when we transition, I think I wrote this here, we can get the recipient out of the get recipient feature. And we can also get the message out of the state that we saved here. And then we just do that code. and then we switch into this final state. If we're in the state, that means we are at here, at this await thing. And so any state that we need later on, like anything that we need to remember for later on, needs to be saved. We don't have a stack. Like normally you store parameters on the stack and they're there for you indefinitely. But here we don't have a stack. So anything that we have previously that we need to remember for later on, we have to store. And because recipient ID is used later on, we have to store that inside of that state. All right, so there are some pretty strange implications of this. Like having a stack is such a fundamental ingrained assumption in our heads from programming that it's very weird to not have that. So I just want to point a few things out about this. Async functions don't have a stack. Again, any state that you are trying to store is stored inside of the future. It is true that there is still a stack, right? The executor thread is still a normal thread. The executor is like normal code. And so that still has a stack. And you do use that to run normal synchronous functions. For example, back here, we had a normal function that was called recipient.verify has space message. And this is called in our poll method. Like in our poll, if we get over here, the control flow gets here, then we call recipient.verify has space. This poll function is being run by the executor, right? This is quote unquote normal Rust, like normal synchronous blocking code. So the executor does still have a stack and you can still call normal functions and that will be on the executor thread stack. But if you want to store state switching between async tasks, that all has to be stored inside of the generated future. This can make debugging really weird if you don't have a stack. Like if you don't have a stack, how are you supposed to get a stack trace or a back trace? Like that is really strange. Fortunately, because Rust stores these things as nested features, and the poll function for the outer one ends up calling poll. I don't think I actually wrote it in here, but it ends up calling poll on the inner features. You still do have stack traces, and if you're curious, there's an article here that kind of explains in a little more detail about why stack traces still work in Rust. But in a lot of other languages, for example, JavaScript, you can have a stack trace that has no beginning because you kind of just didn't save that state and there's no stack to unwind. That's kind of weird. Another very weird thing is you can't have recursion. And that is because the compiler needs to know, it needs to have a bounded fixed size on this state, on the state for this future at compile time. That has to be known at compile time. And if you're recursing, you don't know how many times you're going to recurse. So how big is this supposed to be? Any features that you use have to be inside of here. So we'd have add to inbox state inside of add to inbox state inside of add to inbox state. How many times are you supposed to go? So recursion becomes a little bit trickier. I do think that there are ways to do it, but you have to specify a fixed recursion depth, and it's not quite so pretty. So sometimes you have to convert this recursive code to iterative code. One thing that is really nice about this is that there is almost no overhead. These functions are nearly optimal in terms of memory usage, and you would have a hard time writing this code by hand. This is kind of the code that you would need to write if you were doing this manually in C or C++, but you would get the same performance as you would in Rust, which is very incredible that all of this works, and it's a huge technical accomplishment that took a while to get here. Any questions about this? So I think I have one or two final slides, and let me hide this because, okay, so let's take a step back. Why did we care about this in the first place? Why were we trying to not use threads? So we used threads initially to get some concurrency at all, right? If we wanted to be talking to multiple people, we have one thread talking to each client. But why is that a problem if we're trying to scale up? Yeah, I mean, theoretically, we still have that limitation. We don't have an unlimited amount of memory, but still, threads can consume a lot of memory because they have 8 megabyte stacks. And if you have a ton of these stacks, even if you haven't actually allocated all that physical memory, the operating system still wants to make sure that you could allocate it if you actually ended up using the full stack in each thread. And so there are some memory usage issues. There is also unnecessary context switching cost. So if you are in a thread and you get on the CPU and like the first thing that you need to do is wait for IO, then you're going to switch to a different thread. That thread gets on the CPU. First thing it needs to do is wait for IO, switch to another thread. And if you're like constantly context switching between thousands and thousands of threads, that's going to be a pretty big performance hit. So when does it make sense to write async code? The answer is not all the time. Okay, this is not like, I'm not saying that you should stop using threads anymore, because threads are still great and they solve a lot of problems for us. Async code makes the most sense, like with this in mind, when you need a very high degree of concurrency. So if you only have like, 100 threads, then just use threads. It's not that big of a deal. You don't have that many stacks, life is fine. And when your work is primarily IO bound. Okay, this context switching overhead that I talked about, that only matters, that's only expensive if you're only using a tiny fraction of your time slice. So if you like get onto the CPU and then you immediately switch to a different thread, well, like if the amount of time that you are on the CPU doing useful work is the same as the time it takes for the kernel to switch context, to switch threads, that means that like 50% of your time is being consumed by context switching. That's really, really expensive. So if you're only using a tiny fraction of your time slice, then it makes sense to like reuse a thread to do multiple things. But if you're doing a lot of work on the CPU for an extended period of time, this is actually not such a great thing, because you could end up with a task that is hogging the CPU, doing like some very computationally intensive work. The executor thread is stuck. Like, it called Paul once. Paul went and was like, yippee, let's do some stuff, and like ran some very long computationally intensive thing. And now the executor is like stuck doing that and can't switch to doing other tasks. There's also no benefit, right? Like the context switching cost is so small if you're using full time slices that there's no benefit here, and there is a lot of potential downside. So something to be aware of. Any questions? So this is not a Rust thing, right? I mentioned this in the context of Rust because that's what we're writing, and Rust actually has a really, really nice implementation with a lot of upside and little downside. But you'll encounter this in other languages. So JavaScript is very similar. It's a little bit different in that it does a lot more dynamic memory allocation. So it's not quite as efficient from like a memory usage and memory allocations standpoint. But in JavaScript, if you create a promise, like you create a feature, it starts executing right away. Whereas in Rust, your feature will not actually start executing until you call .await. This is a weird difference where in JavaScript, you can like create two promises and then call .await on both. And those two promises will run concurrently because they start running as soon as you create them. Whereas in Rust, if you create two features and you save them in two variables and then you call .await on both, they run sequentially because they don't actually run until you start calling .await on them. But it's the same idea. It's like almost, besides that one minor difference and like instead of await space whatever, it's like whatever .await, it's almost exactly the same. Go is another increasingly popular systems language, and Go is garbage collected. So its memory model is pretty different. Because it's garbage collected, it's possible to resize the stack of a thread. And so Go has these things called Go routines. They're like, thread-like. You write code in them and it looks like you're just writing normal threads. But under the hood, they're implemented very similar to this. They're not like fixed size at compile time. Like Rust has to know the size of a feature at compile time. Go doesn't do that because it has resizable stacks. They're not taking up like 8 megabytes per task. It just starts very small, and then as you use more memory, it will consume more memory. But that's how it works in Go. And this, I think, is most exciting. One of the reasons that asynchronous programming like this has not taken off is because C and C++ just don't work like this. And everyone uses C and C++. That's just, is part of life. It's kind of how things are. But that's changing. So C++ 20 just got stackless coroutines. It's like experimental compiler support is not all the way there yet. Has lots of sharp edges. I should link there's a blog post. If you look up David Mazier's C++ 20 coroutines, he has a blog post that reviews these. And he's basically like, in classic C++ fashion, there's like 10% great and like 90% razor blades to cut yourself on. But there will be more libraries coming out, hopefully, especially with C++ 23, that will make this easier to use. So definitely a promising area of development, and it works like under the hood is working very similar to Rust. Yeah, some tips that we mentioned last time. For the sake of time, I will just skim through these. I think the biggest thing is like you have to be very careful not to block an async code, because if you do, that is blocking the executor thread, and so it's not going to run anything else, and that's bad. But if you're curious about this, there's a bunch of links here. So there's 2 really great conference talks if you like the video format on like. The first one is more of a high level, like how was this designed? Why did we decide to build things like this? The second one is how does it work under the hood? There's also a good blog post here about like how it's implemented, why it's so fast, how it has like almost no overhead. A few more stuff about like conceptually events, features, threads, and whatnot. And I will add a link in the slides to the David Mazier's post about the C++ 20 features. But yeah, that's it. So stick around if you have any questions. Good luck on the rest of week 10. Hope you all finish strong, and we will see you on Thursday. Thanks so much for coming.